Okay, looks like we're good to go. This week we have Rui Luo from CSIRO 18F. He's a postdoc there, and he is going to tell us about his work. Yeah, well, take it away. I'll let you introduce your own talk.
Okay, thanks. Let me starting sharing my screen. Can you see it?
Yeah.
Okay, let me kick off the. Okay, and thanks everybody for coming. Thanks Emily, Sherry, for having me here. It's great pleasure to present the main results of a Nature paper which was published in end of October this year. And as you know, it's a new repeater we confirmed by fast telescope. We found a lot of interesting polarization feature. And now I will be presenting on behalf of the fast collaboration, including many engineers and astronomers from the NOC and Peking University, even though I'm staff in STIO. Okay, and it's outline of this talk, and basically I will review the backgrounds of some FRB, especially for repeating bursts. And at very beginning, and later I will show the whole story why we do the observation and how we write proposal and carry out observations. And after that, we got very interesting results. That's diversity of polarization, position, angle swing, and arm variation. And we can constrain the theoretical model with the new discovery. In the end, I will summarize all the results. And for fast readables, I don't want to talk a lot on this because everybody in this meeting knows it's very rare. It's a short duration radio transient with prominent flux density. And the more important feature is dispersion and secondary scintillation from what you observe in the dynamic spectrum. And in addition, we have polarization measurements and from some of FRB, but it depends the signal to noise ratio of that burst, as well as your calibration. And now we have 22 repeater published, and whether all FRB repeat is still open question. And according to the petition, we can classify FRB as repeaters and apparent non-repeaters. For apparent non-repeaters, you can expect to have one detection in random position of the sky map. And even though you follow up with a large amount of time, but you didn't detect any additional bursts, and we just put and we define as an apparent non-repeater. It doesn't mean it's truly a non-repeater because we maybe due to sensitivity or other factor you may lose the opportunity to detect repeating bursts. But for repeater, it's very straightforward. If you monitor the targets and with the same position, you may detect multiple bursts, a series of bursts that occurs in with different time with the same DM value. And we can reinforce confirm the same progenitor. And let me review the history of the repeating FRB findings. And first, the repeater was found in the PR survey of a stable telescope. Even though a stable retired now, its achievement on the repeating burst is non-negligible. And after they detect the FRB 121102, and they did follow up for that target and found 11 additional bursts in 2016. And after that, RLA helped us to localize the repeating burst, and the host galaxy has been identified as a dwarf star-forming galaxy at about redshift 0.2. And the second repeater was reported by CHIME, and it shows some interesting feature like down frequency drifting. You can see here, and in the end of last year and early this year, and CHIME almost published 17 new repeating bursts. And in addition, we have some repeater from the other telescope. ASKAP detects 2 repeater sources. So the repeaters show a very different features. The first event is extremely bright. However, the left events of this repeater are not so bright. And for the nearest repeating burst, 1907-11, it show very strange feature, and you can see that it detects in the ultra wideband receiver, the emission only located as in a band limited here, and now we have many repeating bursts, and how to answer that question if all of them repeat. And my PhD thesis is about the FRB statistics, and when I plot such as dispersion, fluence, or flux diagram, I found something is very interesting, and most of repeating bursts located in the bottom left of this diagram. And even with that, I cannot confirm something if all of the repeaters share very faint feature. And well, when I have the luminosity function in units of the event rate density, I found and cataclysmic events cannot account for all of FRB population. And maybe the neutron star module can account for a very bright FRB, but how to deal with the FRB below 10 to 43 erg per second. And now we have so many repeater published, and we can still process. We found something similar with what we inferred before, and this shows plausible clustering in this dispersion flux diagram. And even though we don't know if all of them repeat, but we can have some implication from these diagrams. They might be unconfirmed repeater in the known sample. So, but we need to have very sensitive instrument to review them. That's why we wanted to write a faster proposal in last year. And let me review the fastest basic parameter here. The spherical aperture is 500 meter, as you can know from the name. But the parabolic surface aperture is about 300 meter. And because of this, we developed the active reflector technology. It can help us track the targets for a few hours. And the sky cover of the fast telescope is not may focus on the northern hemisphere, northern sky. It can be ranged in the declination from -15 to 65 degree, and the operating frequency may located in low and middle frequency range. And the beam size of the L band received is about 3 arc-minute. It's not too large, but it's better than the Parkes and Green Band. And sensitivity is high enough. And we know the system temperature has been cooled down to 25 Kelvin. And most importantly, we have installed the 19 beam receiver, which was built in SIO. And we found this all of beamformer are very rare, and with that we can do a lot of things, as for example, pulsar and FRB survey, as well as H1. And now the backends available can be listed here, and we have some background based on Roach 2, Crane, and VLBI and SETI. And there's no available information for VLBI and SETI because I think they are still in developing. But for the FRB and the pulsar observation, we mainly used Roach 2 to record our data. The bandwidth is about 500 megahertz. We have 4,000 channel, And you have three options for the sampling time from 50 to 200 microseconds. And it can be recorded with full polarization, and the data formats in all phase. And here's a proposal. And even though FAST claim that they will be open to the astronomer worldwide next year, but in last year it's still in commissioning, and this shared risk proposal is only open to the domestic astronomer. And when I was PhD student there, and I wrote such proposal to handful repeating candidates, handful repeater in the known sample. I select four sources here. It's from the sources are from Greenbank and Alcebo, Archimos, and Parks. And I was very ready to request 20 hours, and I want to observe each with 5 hours, but it's not realistic because that's in shared risk observation, the observing time is very limited, and that's why I got very not so good grades and grade B. And my requested observing time was reduced to 2 hours. And so many referees feel pessimistic on this proposal because they think, oh, even though you have selected some candidates, but you cannot ensure they repeat indeed. And even though it's repeated, how do you ensure you can observe, you can have yield detection, because FRB has active and inactive phase and duty cycle, and some FRB show non-Poissonier process. And even that, they still gave me 2 hours. And even with 2 hours, we still have we can do many things. And what I want to do is to draw all in one target, and the target was selected here. And when I consider the many factors, I found for Parks FRB, we have very good beam coverage, and the beam coverage reach almost 30%. That means we have 30% chance to point towards the right position. And I have additional reminder from some Parks observer. They told me the position of Parks FRB since 2018 are rather accurate. And that's why I made my final decision to make use of 2 hours to observe this target. And let me review the FRB properties here. And this FRB was discovered by Danny Price in the breakthrough listen observation by Parks Telescope. And from this waterfall plot, we can see the back limited feature that's similar with what I mentioned for ASKAP repeater. And that's the one reason why we pick that. And the other reason is that we found that the M value is rather high, even though it's not comparable with FRB 121102, but with high M, we may expect it's a repeater because it may be located in a dense plasma environment. And after that, and the first observation was performed on 16th July last year. Here's a snapshot I took at the FAST control room. And don't worry, I didn't make any radio frequency interference because the control room is totally radio block. And and after observation, the first observing, we downloaded the data from the backend and to do data reduction. Our searching pipeline is based on the search software called BEAR. It's burst emission automatic Roger. It was developed by KJ and Yingpeng, who is now a postdoctor at MPI. And its pipeline is very similar with the traditional single pulse search. Basically, we have mitigation in the first step, and after that, we will do de-dispersion and get candidates. And once we do candidates clustering, we can select them and only the candidates with a high SNR can be selected. And these candidates and all of candidates can be plotted like this. And the first step is to excise R5. And as you know, even though FAST is located in really quiet zone, the R5 environment is not perfect because we have as many much R5 from satellites, and especially from the Beidou navigation satellites of China. And you can see that R5 environment in the L band there are several spikes here. And to mitigate that for the broadband R5, and we adopt the ZODM match filter, and we just do summation of the frequency channel and to get ZODM time series, and we just excise the spike in the ZODM time series. For the narrowband R5, we just flag them in the bandpass and zap them, and you can see it's there's zap the bandpass here. And after that, we did de-dispersion, and we used as optimized subband method, which is based on CPU, and it can produce real-time candidates. It's not coherent, but it's for repeating FRB, as we know the DM value, that dispersion is enough to help us to get the right DM value. And after that, once you do have such subband dispersion, you will get the candidates. We use match filter to obtain the right DM value. That's maximizing the signal to noise ratio. And here's the candidates number here, and we can find that in the plot on the left, there are about 20,000 candidates. It's not too large number, and even that you can in our pipeline we have the ranking strategy that puts all of candidates parameter in such statistics diagram. You can view the candidate with high ranking can be viewed in such diagram. Even that, since the candidates number is too large, we can inspect them one by one, and very luckily we detect radio burst and on beam 7. And here you can see beam 7 is located in the Parkes beam size, which was denoted as the black circle here. And that means Parkes position is absolutely accurate. And the only 28% chance really happened. That makes our very excited on these results. And actually, it's not one single burst. We detect 4 repeating bursts in the initial observation. And in that particular observing, we didn't require full polarization data because we don't know if that's repeated indeed. And even that we confirm this is a repeater with 4 significant bursts. And after that, we carry out a follow-up for the new repeater and with 4 polarization recorded. And we detect additional 11 bursts. You can see it for some burst in the waterfall plot, you can see the down frequency drifting here. Even though the de-dispersion is not so good, but you can still see that. In total, we detected 15 bursts. All of them are all of them show very narrow band emission, and And as we mentioned before, the only repeater show very bad limited feature, and even some repeating bursts exhibit down frequency drifting. You can see here, and that's why for repeating detection, you have to do dispersion with two methods. One is to maximize the signal to noise ratio. The other is to maximize the complexity of structure. That which was mentioned in Jason's paper last year. And now we have many bursts, and for some of them we have full polarized recorded, and we can do data analysis for the polarization measurement. And to demonstrate if fast telescope is capable to do that, we had such polarimetric stability test. And we want to just test if the target is on or off the beam center, if the polarization data has been recorded correctly. We found for on and off beam center, the polarization profile of particular pulsar here remains identical with each other, even for observing in the next day, and the polarization profile didn't revolve. And when compared with the known observation that has been done by Park's telescope, in this paper, we have found the position angle curve and as well as the pulse profile are almost the same. But the fast telescope is much more sensitive, and you can see that noise level is extremely lower than Park's telescope. That's why we feel confident on our polarization measurement. And since we have linear polarization measurements, we can you can do a rotation. We can get the rotation measure, and as we know, the rotation measure is such a feature can be describing as electrical vector rotate when the radio wave propagates through magnetized interstellar medium. And you can see there's a Stokes parameter curve of FRB 121102, and it can be fitted by a sine function. And as the curve oscillated very intensively. That's why we found the M value is extremely high. And for the M calculation, basically we carry out similar thing with the first repeated paper. We do Q and U fitting using Bayesian inference. We build the likelihood function and run and get the posterior of M value. But to double check if our methods is correct, we still used a very traditional method called M synthesis, and it can help us to get the M value from this Faraday dispersion function. And the M value measures can be listed in this table. You can find for both methods, the M value is quite consistent with each other. But the M value is deviated from the previous observation carried out by Danny Price. They measured M value as 3,000, but now we only have 540. What happened? Maybe there's something wrong in their calibration. When I asked Danny, they told me that their detection is very has not so high signal to noise ratio, and it's also it's also bad limited, and the arm calibration or the polarization calibration they have done is not so convincing. And even that we don't know if there's arm evolution from last detection. And the linear polarization here is very high, but not 100%. And the DM value we measured is consistent with the initial detection by Danny Price. But the DM of DM alive are quite identical, even though we detect the burst at different epochs. And with such, with 15 detections, we can study statistics. We used the Weibull distribution to measure burst rates. We found the burst rate is about 1.2 per hour. And the shape parameter here is very close to 1. That may indicate and say the waiting time distribution can be well described by the Poisson process. And this, now let's go to the main results. And as I mentioned, we have very good polarization measurements. Here's the polarized pulse profile from the 7 bright bursts here. And you can see that for PA curve, you can see on the flat, upwards, downwards, and even S shape. It shows very diversity feature here. And we didn't have such observation before. And this discovery challenges some emission model a lot. And we don't know, even I asked Dick Manchester, who is very experienced in pulsar observation. He told me the such PA swing diversity is very unusual for pulsars, because for many pulsars, you basically have the integrated pulse profile. We don't know, we don't have very good study on the single pulse. I'm not sure if RRAS shows exhibit such PA swing diversity. And for the arm value, as we measure the arm value of different bursts, we can plot the arm variation here. And we found the arm arrived shortly in a short time, and maybe with 10% amplitude. And we don't know what it was caused by. And even though there are arm variation from the first repeater, but this in such short duration variation is the first time we have found. And and until now, we do not have any good explanation on this. And for model constraints, as I mentioned, from a diversity PA swing, it challenges a model form that's proposed by some people who put such a scenario. The FRB should be produced in synchrotron maser, and it can be the GRB-like model. And once the relativistic shock propagates through the ambient medium, and with interaction with interstellar medium, and the plasma will be accelerated, and it can produce coherent radio emission. In such a scenario, the difficulty is that even for the same wavefront of shock, and it's difficult to produce a diverse PA swing, because from the same wavelength, the PA curve is supposed to be very flat. But for the pulsar-like scenario, as we show here, if you put the FRB in a magnetosphere of the neutron star or magneta, you can expect to have a very different PA swing, because the emission could come from different regions. And when we compare the different the scenario here, we found only our results and can account for the and then only the magnetospherical scenario can account for our discovery here. And one thing I want to mention that from apparent non-repeater discovered by ASKAP, they also found such PA swing and like S shape, but it's just one burst. And in our paper, we shows that almost the diversity property of the PA swing. And to summarize, we confirm a new repeater from the known FRB sample with a faster test goal. And we found the diversity of PA swing, and that is very unusual from pulsar or any other objects, but it favors the magnetosphere origin of radium emission. And the arm faster variation may imply the variable magnetized environmental FRB progenitor. And now we are working on the localization. And actually, this work was led by Shivani Bandri, and we detect repeating bursts from galaxy. And now we are still drafting the paper. I cannot tell you too much on that. And that's end. And I stop here to take question.
Thank you very much for this fascinating results. I see Daniela already had his hands up and Sigi as well. So let's go first with Daniela.
Yeah, hi Rui.
Hi.
It's Daniele Michelier. Yeah, fantastic result. I am a bit surprised, well, actually very surprised to see the rotation measure that changes so much within a few hours that you can measure it. And I'm a bit suspicious that, you know, if you use like slightly incorrect RM values, it could cause like wonky polarization angle curves that are like not real, but just because you're using the wrong RM. I was curious if you tried to use, for example, the RM that you measure for the first burst, which is almost 100% polarized, and basically derotate all of the bars to the same RM and see if the PA curves change at all.
Sorry, you mentioned the first burst. Which one? Is Danny Price, in Danny Price paper, or?
In your paper, maybe you can show the plot. It was, I think, a couple of slides after this.
Which one?
After
this one?
No, there were all the bursts with all the polarization profiles.
PA swing, right?
Yeah, exactly.
Yeah.
Yeah, exactly. If you look at the first burst, it's the polarization.
It's very flat.
Yeah, exactly. And for others, the polarization fraction is lower, and the PA is like the swing is larger, except for the last one, which is very interesting. But anyway, my suggestion was that you could use the RM of the first burst and apply the same RM to all of them, and see what happens if it flattens the PAs.
Oh,
we didn't. Like that?
We didn't do that, but it's a good point. And we double check a lot on as a polarimetric for fast test goal. But even for arm measurements, we use in this arm variation plot, we can see that we just adopt the dispersion measure for particular burst. And even though we have this DM value from different bursts, if we fix the DM from the particular burst, we can still get arm variation like that. And that's demonstrating for our arm measurements. But for this this suggestion, we didn't consider that. Indeed.
Maybe you can give it a shot and let me know if this changes things.
Yes, I will give feedback to our team, and and say it's teamwork, and this polarization measurements were not done by myself alone, and we have a lot of discussing on that.
Yeah, absolutely, I understand. Even though this is probably
thank you for your suggestion. I may give feedback to the team member.
No problem. Nice work.
Yeah, thank you.
Okay, and then Sigi.
Yes, thanks for a great talk. I was wondering, it sounds like from how you described the process of selecting the target, it was quite random that you selected this target. So do you think that if you any FRB that you follow up with fast, will it be a repeater?
Only this one I can tell you that. And it's something we do want to search for all repeater hidden in the known sample. It's our main purpose exactly. However, it's many things we have to consider. The basic factor is beam carriage. It's fast 19 beam and each have about 3 arc minutes. But for the beam size of the other telescope is different. And even though the 19 beam can cover a very wide range in the space, but there's a gap between each beam. That's why for this work, we're gonna say we are extremely lucky to detect the burst, even though we suspect it should be a repeater because it has very bad limited feature and the R value is pretty high. But and I'm gonna say even though we want to detect all of detect the repeater from all of known sample, but we have no 100% to conduct it. So now I think we still carry out hunting for repeater in the latest fast observation. I'm not sure. I don't know how it was going yet. But one thing I can tell you, we didn't detect new repeater again.
Okay, thank you. If I can ask a follow-up question too, are you 100% convinced that this FRB is actually the same source as the Price et al. Source, given these beam uncertainties and also?
Yes. The beam, as I mentioned here, in the location we got here, the burst came from the beam 7, and you can see that its beam 7 is totally covered by the initial Parkes beam. And even that, we found the DM value is almost identical to the initial detection by Danny Price. And that's why we claim it's the same source.
Okay, thank you.
And one thing I can tell you, Danny Price performed the new Parkes operation with UWL receiver. They also detect a lot of bursts from that source, and his burst. He confirmed that it's his burst.
Okay, and then Mohit has a question.
Actually, I have a couple of questions. I'll ask first, and then if somebody else has any question, then I can just skip it for the subsequent turns. So first of all, that's great, Raw, the results that you have showed us. So my first question is, I think, related to this Price et al. Burst. So he found the RM he estimated for the burst has a different sign. And if, for example, we believe the rotation measure that you got from, I think, from the observations using FAST, then that RM, they should detect that RM in their RM analysis because their, I think, data is sensitive.
Yeah, our data is our telescope is very sensitive.
Yeah, and I'm talking about Price data.
Yeah,
in
data.
Price data, they should have also estimated a peak at that RM, at the RM that you found for this source.
So do you mean in arm synthesis?
Okay, let me rephrase my question. I'm sorry.
Yeah,
so
sorry.
You said that this FRB is basic. You detected repeating burst from the FRB that Price et al. First discovered, isn't it?
Yeah.
Yes. So in that, I think the RM that they found is negative some value, negative.
Yeah, negative value. I know what you mentioned.
Yes.
That means the direction change.
Yeah,
but
exactly.
But what I want to why I talk a lot on the first event that carried out by Danny Price, because they are not so confident on the arm measurements. As you can find that in this pulse profile, they do not have very good linear polarization measurements. And even in that such band limited detection, it's not enough, it's not sufficient to get very good, very accurate RM value. Even though they did have something like that, RM synthesis around -3,000, but they are not confident on the results. They admit that. And in our measurements, and all of the calibration has been done by KJ Lee, who is very confident on his calibration. And even though we didn't discuss a lot on the comparison RM value from different papers, but we gotta say our RM value is more convincing, because PAX we have very good signal to noise ratio detection. You can see that we have maybe above 100, but for the Dennis detection, they only have 16. It's much lower than that. They still feel very pessimistic on their polarization measurements because of the low SNR and as well as band limited emission.
Okay. No.
Does it make sense to your question?
Oh yeah. So I was just wondering, they should have detected at least a small peak in their RM synthesis analysis at the rotation measure.
We didn't detect any small peak, as you can see here.
In their plot, in Price.
Daniel Price. Yeah.
Yes.
I'm not sure if they detect multiple peak. And they have multiple peak, but they only picked the one around -3,100 units.
But I agree with you. Your detection is much more confident. It's just that associating these two.
Thanks.
Burst. And I have another question, but I'll wait. If somebody else wants to ask questions, then they can go first.
Okay, maybe we can take one from Ryan and then come back to Mohit.
Thanks.
Thanks, Mohit. Yeah, actually, I have a question on the topic of polarization. So yeah, well, actually, on the topic of the Price results for the RM detection, I think I wouldn't. I don't know. My personal opinion is I wouldn't carry too much weight in the RM measurement. Just looking at the Stokes profiles, Stokes Q profiles, you can see that there's a lot of weird artifacts there that would indicate that the calibration hasn't necessarily been done perfectly.
Thank you for this comment. It's another proof for the previous detection, and even you can see that Q and U it cannot be fitted by sign function perfectly, and especially from here the Q curve here is very weird, but they still fit that like this.
Yeah, exactly. So I actually have a question on your results with polarization. I was wondering if you see any sort of evidence of there being a correlation between rotation measure and polarized fraction for the bursts where you do have polarized.
No, yet we haven't get such correlation because our papers mainly reported the detection, and for possible correlation, maybe it needs further study. We didn't have some correlation study on that. And why do you have such suspicion? Is it physical? Is it some physical reason that can be correlated or not?
Well, yeah. So I'm wondering, I suppose, on one level, is the variability in the polarized fraction intrinsic to the source, or second option, is it introduced by the fact that the fitted RM is actually maybe incorrect for some bursts, which could introduce a a difference in the polarized fraction. Or maybe the third option, which is maybe the most interesting, is that is it introduced by depolarization in a foreground scattering medium. And I suppose you don't have any sort of measurements of the scattering on these
Yeah,
bursts.
exactly. There's no very good scattering measurements. It only puts up limits here.
Yeah. Okay. Yeah. So I guess food for future work.
Yeah. Thank you for comment. It's very constructive.
Thank you very much.
Back to Mohit.
Thank you, Cherry, and thank you, Ryan. So my another question is related to the synchrotron maser shock model that you tried to construct in the paper.
Yeah.
I do understand that. Yeah, exactly. So I do understand that in I think in 2019 paper, Metzger used a simple, I think, highly magnetized neutron star, where they claim that in their model, they assume that far away from the light cylinder, I think around radius 10 to the power 11 or 12 centimeter, the configuration of magnetic field is toroidal. So it means that basically the field is perpendicular to the radial vector r. So you should not expect any change in polarization angle. But then that is a simple model they explicitly mention in that paper. I'm just wondering, let's say, because in their model, they invoke shocks, and shocks are infamous or famous for changing the field orientation. So isn't it possible that in the case of this FRB, we already seen that the rotation measure there is a rotation measure excess, then maybe because of the shock, the field orientation is changed and it is no longer toroidal. That's why you see the change in position angle.
Oh, you mentioned Brian Metzger proposed a new model that can account for the diversity of PA swing. I know he mentioned in the Facebook when he replied to Bing Zhang in such a paper post. But in such a picture, the polarization angle supposed to be flat, and it's different from any pulsar-like object. For GRB people, they do like that, but as we mentioned here, if that when we compare it, not only PA swing but also afterglow, in such model, such scenario, we can expect to have as afterglow measurements, maybe from gamma ray or X-ray. But from magnetospherical, they should have some multi-wavelengths observation, but the flux is very limited when the object is located at cosmological distance. That's one argument on that's not so positive to the synchrotron maser. And as you mentioned, there's something about toroidal magnetic field. I actually, I'm not a very theoretical guy. I cannot answer that at this moment. Maybe it's too. I should maybe if you have a question, maybe I can help you to send around the question to Bing Zhang. Maybe he can unpause the question.
Oh, thank you very much. Yeah, I can directly contact him as well. I discussed something related.
Yes, it's very interesting question, and now also our finding, it seems to challenge the existing model, especially from GRB people, and and in such scenario, we cannot expect repeating events because most of GRB like model are based on the cataclysmic events. But for the pulsar-like, it can be repeatable. The events can be produced in the magnetosphere and with extremely high magnetic fields.
So, so back to your table, what is the, because I also read the paper and you didn't explain this thing there. So I was just thinking why you think that if you see why you expect nearly flat PA from Mesa synchrotron model if you do not consider this toroidal field configuration?
Yeah, your point is very physical. I think for many theoretical astrophysicists, they can change model according to particular observations. Even though I don't mean they are cheating, for any model, also this progenitor issue or even emission issue, they are all open questions in the current FRB science. And we don't have the true answer to all of them.
Yeah, thank you. I couldn't agree with you more.
That's what I can answer. Yeah.
Any further questions? Well, if not, we can thank Rui again.
Thank you so much.
Thanks a lot.